Hi everyone and welcome to this webinar entitled IEEE 802.11be, almost all you need to know about Wi-Fi 7. My goal for today is to tell you all about the essentials of next generation Wi-Fi in less than an hour. So this will entail touching upon several intertwined topics. We will learn a bit about the history of Wi-Fi and how it has evolved to present day 802.11ax or Wi-Fi 6. We'll understand what motivates a further evolution towards 11be or Wi-Fi 7. We'll also review in detail the new candidate features in next generation Wi-Fi from a technical standpoint, and some of them we'll see can be seen as direct upgrades over 11ax, whereas others are truly disruptive new ideas. We'll also go through some new performance evaluation results to also appreciate the potential improvements brought about by such new features. Give me a moment to introduce myself before kicking off. I'm Gio, I'm an assistant professor at UPF in Barcelona and a wireless communications expert. I've been lucky to collaborate with other Wi-Fi experts, and here I'd like to acknowledge the great contributions of my colleagues from Nokia Bell Labs, UPF and Rice University. So, Wi-Fi. After a couple of years of COVID restrictions, we can hardly overstate the importance of Wi-Fi for businesses, for entertainment, for social relations, etc. Right? So, Wi-Fi has some clear advantages with respect to other wireless technologies. First of all, it's the use of the spectrum, which is free, or better said, license exempt, which means that the spectrum comes without having to buy a license. Moreover, new bands up to 1.2 GHz in some countries are progressively becoming available in the 6 GHz spectrum. We'll say more about that later. And secondly, Wi-Fi devices are widely diffused. There are like 16 billion installed devices worldwide. So let's say an average of 2 Wi-Fi devices per person, and Wi-Fi is the king technology indoor, both for residential and for enterprise or industrial deployments. According to available studies, Wi-Fi is expected to generate a global value of almost $5 trillion by 2025. So these advantages bring along some challenges though, because new digital applications are adding more and more stringent requirements in terms of capacity, delay and reliability. So increasing capacity in Wi-Fi is somewhat a traditional problem, whereas targeting low latency and high reliability is a paradigm shift. So for those of you who are not familiar with Wi-Fi and the fundamental operating principles of Wi-Fi, there's one thing that I want you to know before getting started with the technical stuff, and it's the channel access mechanism in Wi-Fi, which is based on CSMACA. So CSMACA stands for Carrier Sense Multiple Access with Collision Avoidance. So because Wi-Fi operates in this license-exempt bands, there may be several devices in a given area that try to access the spectrum for their transmissions, and such access needs to be regulated in a fair manner. So to have a basic idea about CSMACA, you can imagine yourself in a conference call. So if you have something to say, you will first make sure nobody else is talking. And as soon as you detect that the current speaker has finished talking, then you will wait for a certain short amount of time, and then you'll try to speak, hoping that nobody else starts speaking exactly at the same time, generating a collision. So similarly in Wi-Fi, a device will have to wait until no other transmissions are detected on a certain channel. Then a random backoff counter is activated, and it is decreased progressively as the medium keeps being idle. Once the counter reaches 0, the device may finally transmit. So this process is illustrated in the figure, where access point 1 happens to be the first one to transmit, and access points 2 and 3 will have to defer their transmissions. This contention process causes delay and also uncertainty, since the waiting time is random and cannot be predicted. Also, this waiting time depends on the activity of other devices in the neighborhood, pretty much like the activity of other speakers in a conference call, as I described previously. So now that we know the very basic channel access mechanism of Wi-Fi, we can better understand what the next evolution will try to improve and why. So the technical name for the new Wi-Fi standard is 802.11be, Extremely High Throughput, EHT. But despite the name, this amendment will be much more than high peak data rates. So of course, yes, that's true that 11be is projected to support at least 30 gigabits per second per access point, which is about 4 times as fast as current Wi-Fi 6. However, the 11be task group also recognized the need for lower latency and higher reliability. This is to enable time-sensitive networking use cases. And last but not least, backward compatibility and fair coexistence with previous 802.11 devices were also listed among the objectives. So looking at the timeline, the extremely high throughput EHT topic interest group and the study group were formed back in 2018. So these initial activities contributed to the creation of the project authorization request. Then this was followed by the formation of the 11B task group in 2019. So the standardization process will take place through several successive drafts, and the certification of the first 11B products is expected in 2024, as you can see on this slide. So you see there are two parallel streams on this slide. The one on top, running horizontally, is the activity of the IEEE 802.11 group, and the one at the bottom, also running horizontally, is the activity of the Wi-Fi Alliance. Regarding the IEEE 802.11 and the development of the amendment, to speed this up, the standard group agreed to first place the spotlight on a set of high priority features, and postponing the remaining ones. So the main criteria being considered to prioritize features are their gain complexity ratio, their time to standardize and time to implement, also the associated interest and market needs. This timeline and the list and the subdivision into releases that you see on this slide is constantly evolving. In parallel, at the bottom, the Wi-Fi Alliance will take care of certifying products, ensuring basically with a Wi-Fi seal that they are compliant to a corresponding IEEE 802.11 amendment, in this case 11B, which is the focus of this talk. So some of the features that will be present in next generation Wi-Fi are direct upgrades over the current standard 11AX, whereas others are more disruptive changes. So for the sake of clarity, I divided these new candidate features in 5 bullets in this slide. The first 3 bullets concern the bandwidth, resource unit allocation, spatial multiplexing, modulation coding schemes. And the last 2 bullets include some disruptive improvements that are associated to respectively multi-link operations and multi-access point coordination. So in what follows, we'll go through each and every one of them. The first feature I'm going to describe is the allocation of up to 320 MHz bandwidth per access point, along with a more efficient utilization of non-contiguous spectrum. So for 20 years, Wi-Fi has been working over 2 bands, the 2.4 and the 5 GHz band. But since 2020, several countries have been clearing the way for a third band, which is the 6 GHz band. So the 1.2 GHz that will be available in the 6 GHz band is actually more than double than we currently have available in the 5 GHz band. So this is remarkable. And also, since only the Wi-Fi 6E and Wi-Fi 7 devices, meaning new generation devices, will be able to operate in this 6 GHz band, they will avail, at least at the beginning, of a pristine and low interference setting. So this new spectrum obviously opens up new possibilities, such as using extremely wide channels through what is called channel bonding. So channel bonding allows to use multiple channels to achieve higher transmission rates and therefore higher throughput and also lower delay. So in 11AX or Wi-Fi 6, access points and stations can adaptively select the bandwidth for each transmitted frame. There is a defined set of embedded channels with primary and secondary channels. So having accessed the medium in a primary 20 MHz subchannel, a certain device can expand the bandwidth by some iterative concatenation of secondary channels as long as they are idle. So in other words, if the secondary 20 MHz channel is idle, then the station can transmit in a 40 MHz channel. If both the secondary 20 MHz and the secondary 40 MHz channels are idle, then an 80 MHz channel can be used, and so on and so forth. So since Wi-Fi 7 devices will be able to operate in the 6 GHz band from the beginning, the plan is to increase this maximum channel bonding from 160 MHz to 320 MHz. Looking at the regulatory aspects, the spectrum around the 6 GHz frequency band has been decided to be made available for use to Wi-Fi 6 and following generations. And different countries around the world have already adopted, or they're still considering adopting this bandwidth with different options and different rules. So the new spectrum will give the opportunity to reduce congestion because, as I said, no previous generations of Wi-Fi will operate in this new band. Also, it will have dedicated operating rules. So Channel access will still be based on contention mechanisms as it is for the already existing bands. And the Wi-Fi devices will have to coexist with incumbent services, mainly fixed satellite and point-to-point fixed services. So to this end, 3 categories of devices have been defined with this purpose: the very low power devices, the low power indoor only devices, and the standard power devices. In this last category, 2 mechanisms have been introduced to avoid potential interference towards incumbents. The first one is automatic frequency coordination, where devices will need to share their location periodically, and a centralized system will provide frequencies and maximum power levels to use. And the second mechanism is to avoid the transmission power to be radiated above a 30 degrees elevation angle, and this is because incumbent services are deployed typically significantly above traditional Wi-Fi deployments. So what we have seen so far concerns channel bonding and utilizing large chunks of spectrum, for example, to increase the data rate. However, there's one more feature that is being considered to further improve the utilization efficiency of such available spectrum. This is the possibility to allocate multiple resource units to the same station. So first, let's recall how OFDMA works in 11AX. OFDMA stands for Orthogonal Frequency Division Multiple Access. The idea behind OFDMA is as simple as that multiple devices can be simultaneously scheduled in groups of different subcarriers. So those groups of subcarriers are called resource units, or RUs. So this may reduce the channel access delay and will add some extra flexibility to distribute resources between devices that have different traffic profiles. So they might need more or less resources. So this slide gives 2 examples. The one at the top is an operation in a non-OFDMA mode, and the one at the bottom follows the OFDMA approach that was introduced in 11AX. So in the first case, in the example, the 2 stations, in this case we have access point 1 and then 2 stations, station 1 and station 2, okay? The 2 stations transmit sequentially without OFDMA, whereas in the second case, there is a single but larger OFDMA transmission from both stations. This is triggered by the access point. So then the access point responds to these transmissions with a block acknowledgement. So this second OFDMA approach has a shorter total transmission time, because contention is avoided altogether. And also notice that because now the 2 stations can transmit at the same time, although the transmission takes longer, then the delay and the waiting time is further reduced. In particular, station 2 doesn't have to wait until station 1 has completed its transmission to transmit. So in the previous example, each station was assigned certain resource units or certain frequency tones. So in the scheme on the top right of this slide, you can see the possible ways of assigning resource units, where an 80 MHz channel corresponds to 996 resource units, a 40 MHz channel corresponds to 484 resource units, and so on and so forth. And the smallest division is 26 tones. So different resource unit sizes are very useful to accommodate, as I say, different traffic needs. And in 11AX, the access point can take the scheduler role and therefore decide when to initiate a transmission, both in uplink or downlink, also allocating the corresponding resource units to the selected stations. So for that, the access point requires a channel and buffer information from the stations. So in the example that we see at the bottom of this slide, which is a toy example, we have an access point and 3 stations. The stations have a different amount of traffic. So the access point will reserve the channel first using the RTS-CDS mechanism. It is one mechanism to reserve the channel. Then it will transmit a trigger frame to allocate resource unit to the 3 stations. So station 1 will get the larger resource unit because it has more packets in its buffer. Then after transmission, the access point replies with a multi-user block acknowledgement, right? So all of this is great because each station gets to transmit at the same time according to the traffic needs, but there is still room for improvement if you notice. In fact, we did not use the whole 80 MHz channel that was available. Station 1 got 40 MHz, Station 2 got 20, and Station 3 got half of a 20 MHz channel. We may have wanted to give the remaining half of this 20 MHz channel, for example, to Station 1 to reduce its transmission time further. But we were only able to allocate 1 resource unit to each station. So 1 slice of cake to each station. So as we have seen in the previous example, a key limitation of OFDMA, although OFDMA is great, is that we may end up not using all the channels. And this is because we can only assign a single resource unit to each station. So this restriction may lead to a waste of resources in some cases. In the previous case, the waste of resources was limited, but in scenarios with a small number of stations, it can be significant. On the other hand, if multiple resource units can be allocated to the same station, then that station can use them to send the same data over several resource units, and then it can improve the chances of correct reception, or it may send more data, increasing the throughput, or reducing the delay, etc. So let's look at the example at the bottom of this slide to understand the limitation of FDMA in current 11AX or Wi-Fi 6. So let's assume that the access point only has data for one station. Then the access point can assign only the primary 20 MHz channel to this station. They are usable, they are available. Then the secondary are busy. So and we would have an additional 40 MHz channel available, but this cannot be assigned to the same station. So the transmission towards this same user will not be possible in the two red channels. So the access point will use 3 times less bandwidth than it could. It will use 20 MHz for that station instead of 60. And this is again because only one resource unit per station can be assigned. So to overcome this limitation, 11BE will support the assignment of multiple resource units per station. So let's see how this brings gains in the same example that we just saw. So as before, assume that there is only one station to be served, and the secondary 20 MHz channel is busy, the one in white. So in this case, because we can use multiple resource units, we are able to assign 60 MHz to this station. Because remember, in this case with 11AX, the station would only get the primary 20 MHz channel, but in this example, the station will get 60 MHz, which is a remarkable improvement. Besides frequency and time, one can also leverage the spatial dimension to achieve substantial peak throughput enhancements. And this is the reason why 11BE will be increasing the maximum number of MIMO spatial streams from 8 to 16. This change will be particularly useful for indoor operations because they have a rich scattering environment with high angular spreads, for those of you who are familiar with this, and that will allow more easily to separate information streams in the spatial domain. To better understand this, let's introduce the concepts of MIMO and spatial multiplexing, also because these concepts will be useful when we'll talk about advanced access point coordination techniques towards the end of the webinar. So more antennas and better spatial multiplexing capabilities have been consistently added to Wi-Fi access points over the years. So what can an access point do when available on multiple antennas? The access point could send one single stream of information to a station, focusing its transmission towards the station thanks to its multiple antennas. This is called beamforming. Another option is to transmit multiple streams of information simultaneously to the same station. This is possible if the station is also equipped with multiple antennas. This would be called single-user MIMO. A third option is to transmit to different stations simultaneously and in the same time frequency resource through what's called spatial multiplexing. This is what's illustrated in this slide, where you see on the right a multi-antenna access point transmitting simultaneously to 2 stations. So the uplink of this is a little tricky, so how does it work? In the uplink, which is illustrated at the bottom of the slide, the access point initiates a simultaneous transmission from each of the stations through a trigger frame. So when the multiple stations respond simultaneously with their own packets, the access point applies a spatial matrix filter to the received beams and separates the information contained in each uplink beam. So each multi-user MIMO transmission may have its own modulation encoding set and a different number of spatial streams. So to coordinate uplink multi-user MIMO or uplink OFDMA transmissions, the access point sends a trigger frame to all users. So this trigger frame, as illustrated in the image at the bottom, will indicate the number of spatial streams, the OFDMA allocations, so the frequency, the resource unit sizes of each user. It will also contain power control information, such that individual users can increase or reduce the transmit power according to the distance, for example, from the access point. The access point will also tell the stations when to start and when to stop transmitting, and then once the access point receives the frames from all the stations, it will send them back a block acknowledgement to complete the operation. So this ensures, complying with a certain power, a frequency alignment, and a time synchronization. So many Wi-Fi stakeholders foresee the need to further upgrade the access point spatial multiplexing capabilities in next generation Wi-Fi to accommodate up to 16 spatial streams. So this upgrade obviously has the potential of doubling the spectral efficiency compared to current 11AX. However, one of the bottlenecks as we increase the number of spatial streams and antennas is the channel state information acquisition. So what is that? Well, imagine that you want to send signals to multiple users or multiple stations at the same time on the same frequency. Okay, so you're going to create beams directed in the spatial domain towards each of these stations. In order to do that, you need to know where the stations are. You need to know roughly their direction. This, to be more precise, in a channel with rich scattering, translates into knowing a channel matrix between the access point and the station. So how is this estimated by the access point? Well, you see an example at the bottom of this slide where the access point transmits a null data packet announcement frame, and then a null data packet, and then a trigger frame. So based on this trigger frame, the beamforming, which is the station, estimates the channel and then sends back a feedback frame to the access point. This way the access point knows and estimates the channel. The problem is that these responses are transmitted sequentially, and therefore the approach, which is called explicit channel state information or CSI acquisition, does not scale well as we increase the number of stations that we want to multiplex. For this reason, there have been at least a couple approaches proposed for 11BE to reduce the overhead caused by this CSI acquisition. One of them is to compress the beamforming feedback frame, but of course this would incur a loss of quality for the channel estimation. Another one is to change the approach altogether and using what's called implicit CSI acquisition. So with implicit CSI acquisition, instead of estimating the downlink channel through a downlink trigger frame, we will have an uplink signal transmitted by the station, and then the uplink channel will be estimated by the access point, but because of reciprocity, this is the same as the downlink channel itself, because Wi-Fi operates in TDD mode. So besides increasing the bandwidth up to 320 MHz and beyond, besides increasing the number of spatial streams, as we have already seen, it's quite natural to increase the nominal data rate by increasing the order of modulation, for instance up to 4096 QAM. And this is the next feature I'll briefly describe, followed by hybrid ARQ or HARQ. So for high SINR scenarios, for instance with short-range communications that often occur in Wi-Fi, higher modulation coding schemes can provide higher data rates. However, let's keep in mind that each additional increase in the order of the constellation gives a smaller and smaller gain. For instance, introducing 256 QAM provided a 33% gain with respect to 64 QAM, and then upgrading this to 1024 increased the rates only by 25%. So as we move with 11BE likely towards 4K QAM or 4096 QAM, this will give us only 20% gain. And at the same time, the cost of such small gain is pretty high, because the SNR needed at the receiver side to accept this constellation is about 40 dB. As you can see in the image on the right, the constellation is very, very dense in that case. Such high SNR can be achieved in some particular cases, for instance with beamforming. Okay, so imagine an access point with many antennas which is serving only one station. So in that case, the multiple antennas cannot be used for multi-user transmission because there is only one station. They could be used to amplify the signal and therefore increase the throughput through a high order constellation. And another feature, as I say, that has been considered for possible inclusion in next generation Wi-Fi is HARQ, which stands for Hybrid Automatic Repeat Request. So current Wi-Fi systems work with ARQ, Automatic Repeat Request, as shown in this slide. Basically, they rely on the retransmission of MAC protocol data units when these are not successfully decoded, or simply when an acknowledgement is not received. So as you can see on this slide, through this approach, the receiver would discard any failed MAC PDUs before receiving the retransmitted version. So there is no soft combining or anything, okay? And with the requirements of enhanced reliability and also reduced latency, so multiple companies advocated that 11B should evolve towards hybrid ARQ capabilities or HARQ. So this feature has been considered for possible inclusion in future generations of Wi-Fi. So how does that work? With HARQ, devices that are attempting to decode a retransmitted MPDU do not ignore the previous unsuccessful MPDUs, but instead they combine their soft bits. So this way they can increase the SNR and also increase the probability of decoding the packet correctly. And this is illustrated in the image on this slide. So the HARQ mechanism is already implemented in cellular system. You might be familiar with it. It can provide SINR gains of approximately 4 dB compared to AARQ. But this is on ideal AWGN channels. Like the throughput gains could be very different when we consider realistic Wi-Fi scenarios that have bursty interference and collisions. So importantly, HARQ is also more robust to errors in the estimation of the SNR. What do I mean by that? So a transmitter could select a high modulation encoding scheme opportunistically, irrespective of the actual SNR. The proper MCS would depend on the SNR, obviously, and the capacity of the channel. So if we do this, either the transmission is fast, it works, we're picking a high modulation encoding scheme, and the transmission is fast, or the transmission fails, but the receiver still extracts some information anyway, and we decode the packet with a retransmission, avoiding having to reduce the modulation encoding scheme for the retries, for the retransmission. So this soft combining operation, however, must be said that it requires extra computational capabilities, also memory requirements to store past transmissions, and so further studies are expected to evaluate the performance and also the complexity requirements. So one of the expected revolutionary changes in 11B or in Wi-Fi 7 is the native support of multi-link operations, and this would be hopefully favorable for both high data rates and also low latency. Let's see more about that. So what does multi-link actually mean? We could think of multi-link as multi-band or multi-channel operations, and this is a feature that has attracted a lot of interest so far for multiple practical reasons. Many access points already operate in multiple bands. Many stations already are dual band. A new band will be available in the 6 GHz spectrum. So how to make a more efficient use of all these multiple bands and multiple channels? Here we see a toy example where we have two channels available. In this particular example, one is in the 5 GHz band and one is in the 6 GHz band. So the slide shows an example of multi-link operations across these two bands. And there are several ways to exploit the availability of two different bands. In this slide we see, for example, opportunistic link selection, link aggregation, and full duplex. So we see packets arriving in downlink or in uplink, and they have their own numbering, as you see, number 1, number 2, etc. We see channels marked as busy in gray, used in downlink in yellow, and in uplink in blue, okay? So for instance, for the first packet, which is to be transmitted in downlink, because the 6 GHz channel is free, this is opportunistically selected, while the 5 GHz channel is busy, right? Then for the second packet, both links are available and both could be used simultaneously through link aggregation. So the transmission of this packet is faster because more spectrum is available. And then the 5 GHz band is used opportunistically for the first uplink packet in blue, because the 6 GHz band is occupied at a particular time. And then the same thing occurs for the third downlink packet, okay, which is transmitted on the 5 GHz band, so on and so forth. Then we see that, for instance, for the second uplink packet, this arrives in the queue, and then full duplex transmission is exploited. This packet is transmitted in uplink on the 6 GHz band, while the previous downlink packet is still being received on the 5 GHz band. So there are a lot of options. Now let's assume that we actually want to evaluate the performance of multi-link operation and the gains it provides. Particularly we're interested in the delay reduction. So what we do is we compare three operation modes for simplicity. The first one, the first bullet, is SLO, single link operation. This is a conventional operation mode where we only have one radio interface. You see the diagram on the right, packets arrive, and then we have three different approaches compared, okay? The first one is SLO, there's only one interface. What about the second one? So the second bullet is MLO, multi-link operation, STR. STR stands for simultaneous transmission reception. What this means is that there are two independent radio interfaces. So each interface can start its own back-off counter, and then we can assign packets to the first interface that becomes available, right? What about the third bullet? That's called MLO and STR, so multi-link operation, non-simultaneous transmission reception. In this case, although there are two interfaces, interface number one acts as the primary. There's only one back-off counter on this interface, and then the use of the second interface, which as you see in the diagram, it is depicted in dashed lines. This is conditioned on the first one being available, okay? So because the second one is a secondary interface, it can be used, but only when the first one is also available. So you see an example in the diagram. There are 4 packets, and we see the delay incurred by these packets from their arrival to the transmission in the 3 different cases. We see the baseline, which is SLO, single link operation. Then we see that multi-link operation STR reduces the delay for packets number 1, number 2, and number 4. So in many cases. In the case of non-STR, the delay is reduced for packet 2, but only for packet 2, not for the other cases. And that's again because NSTR has some restrictions. The second channel can only be used condition on the availability of the first one. Okay, so now we wanted to evaluate the delay of multi-link operation. We compare the 3 operation modes that I described in the previous slide. What scenario do we consider? So in our study we consider the scenario depicted at the top right of the slide, where there is a single access point, a single station, so they form this basic service set, alright. There is downlink traffic, which is assumed to be Poisson, and then the load intensity is normalized. We'll see different values for the load intensity. Basically, we feed more or less traffic to the network, and we see what happens. Okay. What about the channel occupancy? This is the interesting bit, because we use channel occupancy from real measurements. These are contained on a dataset called WACA, which is publicly available. And it is the result of a joint effort between University Pompeu Fabra in Barcelona and Rice University in Houston. So this dataset contains real channel measurements in the 5 GHz band. In this particular case, at Camp Nou, which is the football stadium of FC Barcelona, which you might know. We in particular consider channel number 36 and channel number 100 for our study. And you see in the slide at the bottom right examples of traces of occupancy for these channels versus time. So you can see that this follows basically the football game evolution. So the occupancy grows as people go to the stadium before the game starts. Then there's a decrease in occupancy during the game. There's an increase again at halftime. There's a decrease again during the second half. A further increase after the game ends, and then a decrease as people leave the stadium. So the question I will have for you is, do you think that these occupancies are symmetric or asymmetric? What do you think the correlation is between these traces? No, the answer is not so obvious, because it depends on the interval that we consider. But what I can tell you is that in some cases there is correlation, but in some cases there isn't. So it is interesting to study the performance of multi-link operations when the 2 channels that are being used by MLO are symmetric or asymmetric in terms of occupancy. So let's see better what I mean. We start by studying asymmetric occupancy scenario. So in this case, both channels available are idle, so they are free 40%, so they are occupied 40% of the time, okay? So the figure on the right shows you the latency in milliseconds for different traffic load. This traffic load is normalized to the SLO throughput, okay? And this latency, we have 3 different bars of 3 different colors. Blue depicts SLO, single link operation, and then red and yellow depict the 2 different flavors of multi-link operation that we have introduced. Okay, so we're looking at the 95th percentile, which is the 5% worst latency, to assess the worst cases, let's say, or close to the worst case. So what do we observe? Well, so we observe that for single link operation, which is the blue bar, the delay grows with traffic. In particular, the 95 percentile delay grows very rapidly and then it exceeds 100 milliseconds. In the case of MLO STR, which is the red bar, there's almost an order of magnitude reduction in the 95th percentile delay. So really MLO brings dramatic gains. In the case of non-STR, where the second radio interface can only be used in conjunction with the primary one, so there is only one back-off counter, the benefits are confined mostly to the average delay reduction. In terms of worst case delay reduction, we don't do as well as we do in the case of STR. Okay, there are other cases that we studied. If you're interested, you can find them in the paper cited at the bottom right, for low occupancy in both channels and high occupancy on both channels. So these scenarios are a little bit less interesting, because when the occupancy is low on both channels, then both MLO approaches can reduce the delay, and when the occupancy is high on both channels, well, then they cannot do so much, because it's difficult to use the second interface since this is also very often occupied. So the conclusion from this slide would be that the red flavor of MLO, so MLO STR with the two independent interfaces, does very well and is clearly the winner. But is that the case always? So here we see that when we have asymmetric occupancy, there are situations where actually MLO could be detrimental for the delay. Let's see what I mean. So we consider in particular the scenario where the primary channel is occupied 10% of the time, so it's relatively free, but the secondary is much busier, occupied 70% of the time. So in this case, we see that while the yellow bar, MLO and STR, is deterministically better than the blue one, means it deterministically does better than single link operation, that's not true for the red bar, the MLO STR, when we have two independent interfaces. So sometimes the delay is worse than the delay under single link operation. So why is that the case? That happens because sometimes a packet is assigned to the first available channel. So you have two available channels, each has its own back-off counter. So we assign a packet to the first available channel, and then we start decreasing the back-off. But what happens if then this channel that we selected gets occupied later on? Then the back-off counter gets frozen, and if this happens too often, it's frozen for a long period of time, that packet is stuck with that interface, and then it will experience a large delay. So this is what causes the higher 95th percentile delay. There's obviously a way to address this, and it's what we propose under the name of opportunistic MLO STR or STR+. So in this case, when both interfaces are idle, we start a back-off counter on each, and then we allocate the packet to the interface whose back-off counter expires first, right? So this avoids the shortcoming of the red scheme, the MLO STR, which occur under bursty channel occupancy. The performance is shown on this slide on the right through the green bar. So in this case, we see really that MLO STR+, as we propose, reduce the latency also deterministically compared to single link operation. So right, now let's focus on another disruptive framework introduced in 11BE, which is multi-AP coordination. So let's see how this can be applied to enhance the spatial reuse. So access point coordination means what the term itself says in a self-explanatory way. So what we mean is that multiple nearby access points would coordinate over the air all the transmissions in the time and frequency domain. And this is done with the purpose of avoiding channel contention, also improving throughput and worst case latency. Obviously, this entails some extra overheads and some extra complexity. So access point coordination is expected to come in different flavors. There will be low complexity approaches, which we'll talk about, the one based on OFDMA and on spatial reuse, and there will be more advanced approaches which also perhaps will perform better. So the first approach I'll describe is coordinated OFDMA. So with coordinated OFDMA, access points jointly allocate their time frequency resources, and this is particularly attractive to minimize the latency in short packet transmissions, right? Because this reduces the contention time. So now traditionally, the problem to solve when we deploy new Wi-Fi network is to find like an idle chunk of spectrum. But with coordinated FDMA, there is no problem, because even in the case where two basic server sets overlap, we can still coordinate the transmission such that they can, for example, split the band or split the transmissions in time. So by allocating these resources jointly, the two access points once again can minimize collisions and make a more efficient use of the spectrum. And another relatively simple technique for access point coordination is coordinated spatial reuse. This works in the power domain, okay? So let me explain what happens in 11AX, the current Wi-Fi 6 first, and then let's see how this is supposed to be improved in 11BE. So in 11AX, we see the figure at the bottom left. We have two basic service sets, okay? Access point 1 has gained the right to transmit to its own station 1, okay? Then access point 1 will give the possibility to access point 2 to also transmit, as long as access point 2 does not interfere significantly, right? So access point 2 basically needs to reduce its transmit power to comply with a maximum interference threshold, right? So this is okay. The problem is that in this particular example, station 2 falls pretty close to access point 1, and therefore it receives too much interference. So there's basically a collision generated at station 2, so access point 2 cannot really exploit this spatial reuse opportunity. The transmission is wasted. The approach at the bottom right instead, which relies on joint scheduling and joint power allocation, will prevent such uncontrolled collisions, and this is what's supposed to be adopted in 11B. So let's look at the figure at the bottom right. In this case, what happens is the same as before. So access point 1 will grant a transmission opportunity to access point 2, as long as access point 2 controls the transmitted power, but also at the same time access point 1 will reduce its transmit power. So basically access point 1 and access point 2 will jointly agree on the power levels to be used. Of course, this entails coordination, and in this case access point 1 will not interfere significantly to station 2. Okay, so in this case, the transmission to station 2 will occur successfully. So we saw that 11BE plans to take access point coordination and spatial reuse to the next level, but there's much more than what I have told you so far. I'm going to describe now two more sophisticated approaches for access point coordination, which may be somewhat more complicated to implement, might take longer to standardize, right? But they also promise higher gains. These are joint transmission, or MIMO, and coordinated beamforming. So let's start with joint transmission, which is the approach to the left of this slide. This has also been known under different names: network MIMO, DMIMO, coordinated multipoint, etc. So it is the most sophisticated solution in terms of coordination complexity that is being considered. So in DMIMO, or in joint transmissions, non-collocated access points will perform joint data transmission and also joint data reception to and from multiple stations. So compared to systems that have independent access points, this tight inter-access point collaboration can provide extended coverage, because there can be additional beamforming gains, and basically would turn neighboring access points from interferers to servers, which is really great. To achieve these gains, what do we need? Well, we require inter-access point collaboration, because we need to jointly process both the data and the channel state information of all the stations. So we need a high capacity and low latency backhaul, for example, fiber. And this implementation will also require designing a new distributed CSMACA mechanism for channel access, because we need to optimize channel access but also guarantee fair coexistence with independent access points that might be deployed in the same coverage area. So we also need tight synchronization in time, frequency, and phase, because the signals transmitted by different access points to the same station need to add up constructively. So probably one way to achieve this is to implement the MIMO through a master access point that oversees the operation of the whole cluster. So this might compromise the performance gains, but it could be a trade-off, because it will simplify the coordination requirements. The second approach, which is illustrated to the right, is coordinated beamforming, also known as coordinated null steering. So typically multi-antenna access points will use their capability to spatially multiplex stations through spatial multiplexing or multi-user MIMO on the same time frequency resource. We have seen this before. But alternatively, the access points that have multiple antennas can leverage their antennas to place special radiation nulls. So this means to suppress interference on a particular direction. This is similar to beamforming. You can think about beamforming as focusing the signal on a certain direction, whereas null steering or interference suppression is basically suppressing the signal on a certain direction, right? So this is very useful because, as we will see, the access point can make itself invisible to another station and also deaf to the transmissions that are coming from that station. Okay, so you see this illustrated in the figure where access point 1 transmits to station 1 and suppresses the interference generated at station 2. Access point 2 in this particular case exchanges the favor, transmits to station 2 but suppresses the interference generated at station 1. So this will boost spatial reuse because it will enable simultaneous data transmission of devices that are under the same coverage area. Of course, if I'm invisible to my neighbor, then I can transmit while my neighbor is also transmitting. So of course, when this is compared to coordinated OFDMA, it requires a further degree of cooperation, right? But it is simpler than the joint transmission approach illustrated on the left. Because in this case, only channel state information is to be acquired, but not the data to be transmitted to the stations in the other basic service set. So in what follows, I'll show you how coordinated beamforming can really help achieve low latency communications in Wi-Fi. So to show that, let's consider 3 scenarios. The first scenario we consider is a baseline 11AX system that doesn't do anything fancy. It doesn't have any special reuse capability, so the spectrum is shared according to the conventional and classical CSMA-CA. So as you see in the figure at the bottom of the slide, this works according to time sharing, so devices might hear each other, and in that case they need to differ from transmission. So they need to basically alternate their access to the medium. The second approach, the second bullet, the second scenario is again an 11AX system, but in this case we have some coordinated spatial reuse based in the power domain. So we have spatial reused in the power domain, which means that neighboring basic server set might be allowed to take up an opportunity to transmit as long as they don't interfere too much. Okay, so the access point on the left may grant a spatial reuse opportunity to other stations or other access points to the right, and as you can observe in this figure, sometimes this works. For example, the 2 stations located far away from access point 1 at the far right, they can find a spatial reuse opportunity because they're far enough, they don't interfere too much, but some others don't. For example, the ones that are closer to the basic service set on the left, then they cannot because they're too close to their access point, and reducing the power would basically prevent them from having a successful transmission. The third scenario we consider is coordinated beamforming. So what happens in this case? The figure at the bottom of this slide is quite complicated, but all we need to notice is that now there is a placement of radiation nulls. So because now access points are placing radiation nulls, they are making themselves invisible to the other devices, and they're also deaf to the transmission of these devices. So that means that when a spatial reuse opportunity is granted to a nearby device, this nearby device might not even need to reduce its power because thanks to null steering, devices are invisible to each other. Okay, so in this particular example, out of the green set, the stations at the bottom left now is able to find a reuse opportunity even though it's close to access point 1, and that's because access point 1 is placing a radiation null, so it doesn't hear that station. Great, so enough with the description, so let's see what the delay is and what gains this coordinated beamforming provide. So we consider a particular scenario, particular deployment where we have 2 access points. We have 24 stations uniformly distributed, and out of these 24 stations, notice that 16 generate broadband traffic, whereas 8 generate low latency augmented reality traffic. So the uplink broadband traffic is modeled as an FTP service, whereas the low latency traffic is modeled as a augmented reality application. You see the details on the right of the slide. So the access points are equipped with 8 antennas, an array of 4x2 antennas. and they can place radiation nulls as well as multiplexing stations. So basically, they can suppress interference, and they can also increase spatial reuse opportunities thanks to the null placement. So does that pay off? Yes, it does pay off handsomely actually. On the right of this slide, I'm showing you the delay performance achieved in the 3 scenarios. So you see bars in blue for the baseline 11AX, in red for 11AX with power domain spatial reuse, and in yellow, which is what coordinated beamforming might give us. We see different cases, the median latency, and then the 5, 1, and 0.01% worst latencies to check the extreme cases, okay? To also account for reliability. And we see that although the 11AX approach in median, which is like half of the time, guarantees very low latency, below 3 milliseconds, in some bad cases this latency exceeds 200 milliseconds. On the other hand, there's a 1 order of magnitude gain provided by coordinated beamforming even in the worst case. So this is great, and how is this possible? Well, once again, because we have a more aggressive spectrum access, because we have a strong interference mitigation produced by the radiation nulls. Well, one question could be, okay, but what about the throughput of the other devices, the ones that do not have latency sensitive traffic? Is this degraded? Well, it's almost preserved basically, although not shown in the slide. I say almost because there's a very slight reduction in the throughput caused by the fact that now some spatial degrees of freedom of our array are used to suppress interference rather than to increase the beamforming gain. But this is only a slight reduction. Great, so it's time to start wrapping up what we've learned about next generation Wi-Fi. The main takeaway is that the key objective of 11BE is not just to enhance high throughput, but also to reduce worst case latencies, as we have seen all along. And then we have introduced some new candidate features. The first ones were related to a more efficient spectrum utilization, so wider channels but also more efficient use of non-contiguous spectrum available. Then we talked about MIMO enhancements, multiple spatial streams, and so on and so forth. More physical layer improvements, the constellation order, and also potentially hybrid HARQ. Then we introduced one of the star features, which is multi-link operation, and we show the delay reduction that this can trigger, and also some important details about its implementation. And finally, we talked about access point coordination in many different flavors, low complexity, and then more sophisticated ones, showing also some performance result for coordinated beamforming. So for more details, I have listed a few references related to the topics that I covered today in this webinar. In particular, I recommend the first 2 articles because they inspire the content of this webinar, and they also provide more details on the simulation results provided, respectively number 1 on coordinated beamforming and number 2 on multi-link operation. So my goal for today was to tell you all about the essentials of IEEE 802.11be in less than an hour, and I hope I have accomplished that. By now you should better understand the motivation behind an evolution towards Wi-Fi 7. You should know more about the technical features that are likely to be implemented by Wi-Fi in the future, and hopefully you found our novel performance results insightful as I did. It's been a great pleasure for me, and this concludes the webinar. Thank you.